eigen decomposition. So the problem is, for a square matrix, there exists this property of a square matrix, that A of x equals to lambda x. This is just a way to visualize this. As you know, that matrix A stretches and squeezes some parts. So there has to be some x along which the matrix acts linearly, right? So Ax equals to lambda x, where lambda is an eigen value and x is an eigenvector, right? So, if I put all of these eigenvectors as columns in the matrix and the eigenvalues on the diagonal of the matrix, this is what it becomes. So this is an A and this is an xi. This is lambda times xi. So if I write it as A x equals to big lambda x, I'm putting a lambda here. This is what happens. This is my A matrix. This is my X matrix, where each column is an eigenvector. So A times X is lambda times this X, lambda 2 times this another x2, then lambda 3 times. This can also be written as a diagonal lambda 1, lambda 2, lambda 3, and the X matrix here. So this is just a way of writing this, and I can take the inverse of x, given that this is a non-singular matrix and the invertible matrix X. So I can write my lambda as x inverse Ax, so I can write my A as x lambda x inverse, where this writing my A as x lambda x inverse, this is known as a similarity transformation, as you can read. If my matrix is unitary diagonalizable, what that means is that these x, which we saw in the previous slide, those x's are unitary, orthonormal, such that their inverse is the same as their conjugate transpose, their Hermitian. So A is u lambda UH, where, yeah. So the theorem is, if my matrix is normal, that means it conjugates with its Hermitian, that means it's normal, and if it's normal, it's unitary diagonalizable. And symmetric matrices are, again, if A of H, if the Hermitian is equals to A, then A squared, therefore they're like the special cases of normal matrices. So Hermitian matrices are unitary diagonalizable, that's true too. Now I write eigenvectors in such a fashion. For example, I write right eigenvectors and I write left eigenvectors. For example, Ax is lambda x is a right eigenvector, but A Hermitian y is equals to lambda conjugate y. This is a left eigenvector. That's just how it's defined. They are correspondingly left eigenvectors corresponding to the given eigenvalue lambda, as A Hermitian y is lambda conjugate y. That's what I've written here. That's how I define my left eigenvectors. For unitary matrices, obviously the left eigenvectors and the right eigenvectors are the same. They're just special matrices like that. And why are they same? Well, if you look at this, for the Ax equals to lambda x, that's what the right eigenvectors satisfy. X lambda, actually, yeah. Right? So what do the left eigenvectors satisfy? When I take the Hermitian of the same thing, A Hermitian y is equals to y times lambda conjugate, right? Lambda, I can write the lambda Hermitian too in this case. As they are diagonal, I can always write them. So now take the transpose of the Hermitian of this entire thing. Y Hermitian A is equals to lambda Y Hermitian. Y Hermitian A is lambda Y Hermitian. This is the left eigenvectors, right? Now I can write A as Y Hermitian inverse. Y Hermitian inverse. But also I can write the same thing as X inverse, X lambda X inverse. So X inverse is equals to Y Hermitian for a diagonalizable matrix. Yep. Because I wrote A as X lambda X inverse, right? X lambda X inverse. Perfect. Yeah. So comparing these two, yeah. Good. How hard it to find? I mean, my next question is how hard it is to find eigenvectors, eigenvalues numerically. Well, this is a non-linear problem. Why is this a non-linear problem? Because my eigenvalues satisfy this equation. A minus lambda I determinant is equals to 0. So all of those lambdas that satisfy this, so lambdas are the roots of the characteristic polynomial of a matrix. So for any matrix more than 3 dimensions, 4 dimensions, they are like a cubic. Cubic is, I think, solvable, but 4th degree polynomial is not solvable. 5th degree polynomial is not solvable in closed forms. So they cannot be computed. There must be iterative algorithms, for example, which refine your estimate every iteration. That's the kind of algorithm that is needed to calculate eigenvalues. So what is the condition of finding eigenvalues? How well conditioned is this problem? Well, the absolute condition number is 1 over the absolute cosine of angle between x and y, and cosine of angle is between x and y is defined in such a manner. So this condition number is only for a simple eigenvalue. And what does it mean to be a simple eigenvalue? A simple eigenvalue is which has the geometric multiplicity of 1 and the algebraic multiplicity of 1. What does geometric and algebraic multiplicity of 1 mean? Well, algebraic multiplicity means that determinant of A minus lambda I has a root, let's say lambda naught. Well, this lambda naught is only one single root. There is no mention of x minus lambda naught square. For example, if this was my characteristic polynomial, this is how lambda naught looks. It's not this. It's a simple. It has only one occurrence. And geometric multiplicity means if ax equals to lambda x, then ax1 equals to lambda naught x1 and ax2 equals to lambda naught x2, where x1 and x2 are linearly independent. This has a geometric multiplicity of 2. I mean, there are 2 eigenvectors which are linearly independent from each other, but they satisfy this equation. So it has a geometric multiplicity of more than 1, basically. Yeah. So yeah, so only a simple eigenvalue, which means it has an algebraic multiplicity of 1 and a geometric multiplicity of 1. Only for a simple eigenvalue is this the condition number. Even if my matrix was a Hermitian normal matrix, it's not easy to calculate the eigenvalues if it's not a simple eigenvalue, It's a difficult process. So I think so condition of the eigenvalue problem, I can see the proof. I can see the sketch of the proof. If a of x is lambda x, lambda naught is simple, that means determinant of a minus lambda I is the product of their eigenvalues, and so geometric multiplicity is the number of linearly independent eigenvectors of lambda I, and geometric multiplicity is always less than algebraic multiplicity. So a simple eigenvalue is one which has algebraic multiplicity of 1 and therefore geometric multiplicity of 1. So the proof is from Doifelhard that the map that goes from A to lambda A is a differentiable map such that its derivative on a matrix C in a direction C is Cx naught y naught divided by the inner product of x naught and y naught. Right? This is proved by considering a small perturbation in matrix A and differentiating with respect to that perturbation direction. We get that, and the condition number is done in a similar manner. Yeah, okay. It's just a simple thing. Yeah. So in this direction, lambda naught is the supremum of this. Using the Cauchy-Schwarz inequality, you can come up to the cosine shape. Yeah. And the relative number is x upon fx. F prime x is just the number this, and x is the norm of the input, and fx is the norm of the lambda, which is just the absolute value of the lambda. Okay. So perturbations of order delta in the entries of matrix A induce changes of the order delta, I think this has to be a norm, divided by the cosine of the angle between the two eigenvectors. So for normal matrices, A Hermitian, I mean this is a normal matrix which have x naught is y naught, they coincide. Therefore the angle between them is 0 and as the cosine is 1, that means the absolute value is the kappa is the condition number, absolute condition number is 1, which can be considered well condition. Finding non-simple eigenvalues can have very high absolute condition number, but can still be done numerically. This is out of syllabus. Right. So bounding error in eigenvalue computation. Let A be a Hermitian matrix and let lambda be a computed approximation of the eigenvalue eigenvector pair. So this is the truth thing, and this be the computed one. So the residual is A x hat minus lambda hat x hat. This is what the residual is. So it follows that the difference between these residual, the difference between the calculated lambda and all of the other spectrum, all of the other eigenvalues in the spectrum of A, the minimum of this difference is less than equal to this quantity, which is depends on the residual and the true eigenvector. So I think this assumes that we know the true eigenvector. So to do this, we've only assumed that A is a Hermitian matrix. We're only going to look at the Hermitian case. If this is Hermitian, then there exists the orthonormal basis, and these are the eigenbases. So I can write my x hat as alpha times ui, right? And alpha can be done in that manner. R is A x hat minus lambda hat x hat. This can be calculated. A x hat is A acting on this. Alpha can be taken out common, and action on ui will give me lambda I. So it becomes alpha. No, alpha cannot be taken common. Alpha can be excluded while applying A. Alpha lambda ui minus lambda hat x hat is again lambda hat alpha I ui. Take the alpha's common by clubbing this sum. This is the difference. Take the norm of this difference, the norm of this residual, and as they are orthonormal eigenbases, I can only take the sum of squares of this internal term. Divided by x hat. X hat is given by alpha square. So alpha square, this divided by alpha square. If I take the minimum of this element, if I take the minimum of this object and I take it out as a common, this term, the sum of alpha's I squares divided by the entire sum of alpha I squares, this will become a beta which will sum up to 1. And yeah, that sums up to 1, and therefore this is less than equal to, it is greater than equal to the minimum of this number, square, and that is therefore the, okay, yeah. The minimum is less than this. So yeah, this, what's so special about this bound? This is a posteriori bound. That means after I have calculated calculated an eigenvector and an eigenvalue, I can give the error, how far my calculated eigenvalue is from, I think, the one that I wanted to calculate. Okay. So the condition of computing eigenvector xi for an eigenvalue lambda I depends on the separation between the eigenvalues. This can be proved by looking at Quateroni section 5. Yeah. So the condition number of computing eigenvector xi for an eigenvalue depends on the separation between the eigenvalues. If the eigenvalues are very close to each other, that means it's ill conditioned. So I can see that it's 1 upon the minimum of lambda minus lambda j. And to see how this is computed, let's look at Quateroni. Yeah, so I think what they have done here is look at the perturbation in the matrix A and try to bound that, and so analogous to 511, the quantity. Okay, so but my question is, how is this derived? I think this is just a property. Okay, he has just mentioned it. So I guess we can also take it as an axiom and move on. Okay, computing eigenvectors. So computing eigenvectors is a ill-conditioned problem if we have repeated eigenvalues, and yeah, it's very close. I mean, if the eigenvalues are very close to each other, that means it's a bad problem. It's a ill-conditioned problem. So this indicates that even multiple eigenvalues require care. I said that already. Even for Hermitian, let's say the best matrix possible, eigenvectors can be hard to compute. And think about it. For example, if you had an identity matrix, what are the eigenvectors? Every vector is an eigenvector, so I think it makes sense a little bit. Yeah, for an identity matrix, all of these eigenvalues are 1. So every vector is an eigenvector. So what do you give out as an answer? So if a matrix was, let's say, very close to identity with repeated eigenvalues, I think we would have problem giving its eigenvector.